Good morning, Ned. Hello.
Hey, I said, oh, first of all, I'm already on.
Yeah, he was asking for it.
Okay. So what's the sound is on? Hi, Bruce.
Hi.
I'm here.
Okay. I had one of these wonderful, although useless, resets of the computer last night. It's
Oh
just,
no.
you know, well, it's probably updating some stupid, and that just threw everything into chaos here. So let's see. I'm bringing up the. There we go. Okay, so we will share. Hello, we will share. So there we're ready to go. There's our plan for the day. Jairam asked about homework. I'm not going to try to do any of that. Really, you need the MATLAB and stuff. So I'm going to just demonstrate things with it here. And so we will do some problems that we'll have them do on AGC and on this other one, but not this one here. Okay. Oh, Ned left.
No, I'm here. I'm here.
All I see is I saw your face and now I see your name.
Yeah. No, I'm here, Bruce.
All right. Okay.
So it'll go well.
So Ned, have you tried using the
Yeah. Trying using Zoom.
have you tried using the come on, this is not what I want. What is this? This is Word. Ah. Um there's a all right. No, there's a feature where you can annotate on the screen, and it's like you're, let's see, it's like you're writing on the glass,
Right.
and then you go to a different slide, and whatever you wrote on the glass is still there.
Yeah. Oh, I see. Okay.
I was telling them, remember there was a screen in 5.128 that somebody wrote on the actual screen once, so that it was there for.
Oh boy. That happened.
Okay, I guess we're ready to do you need to say anything?
Bruce, you're doing great.
Okay,
People know you, so
away we go here. I'll give them an introduction, okay, and then I'm gonna turn it over and let them do the videos.
Yeah, that sounds like a great plan, Bruce.
Okay. All right. See you later.
Okay, thanks.
Okay, everyone. This is the point we come to the optimal power flow. Now, what I want to say is that this was an application. The first papers on optimal power flow were written by a Frenchman named Jacques Carpentier. I met him a couple times. Very, very gracious gentleman. Worked for EDF, Électricité de France, in France. I don't know if his office was in Paris. I met him in Avignon. It's another city in southern France. And he formulated the problem in the 1960s, early 70s, some time frame like that. And I would say it took at least 25 years of people writing papers and papers and papers and papers, and until good reliable solution methods had been developed. So we're going to have you go through the slides and pardon me, the videos on these, and that would be at least part one. And we might go back and touch part two as well. But you can see that there's the formulating the problem. I'm not going to try to preempt the video because it goes through all of this and what we can do with it. But that there are several simple examples in here. We have an example like this. And we use our old friend, the DC power flow, to model the power system. The OPF is an economic dispatch with the complete model of the power system built into it. So this is the example that we're using. And then what I'm going to do for the problem session portion is I'm going to review with you some examples of actually running this algorithm. So we'll and then we'll possibly we'll touch on the 12B later. So this I would like you to watch both videos if you can, and we'll give you. Let's see, we're supposed to go. I'm going to start just right away, and let you start watching those till 9:45. Please try to watch 12A and 12B or Module 12, Part 1 and Part 2, depending on how they're labeled on the website. And then when we get back, I'm going to have MATLAB loaded up, and we will demonstrate running the modules for you. Both the DC model, the so-called linear power programming model, linear network model, as well as the AC. Okay, so we'll just turn you loose now to watch those video modules, and we will see you in about an hour. So we will stop sharing, and we will turn off the sound. Okay, we're back, or I'm back. Anyway, what I'm going to do is do some demonstrating in lieu of problems today. And so let's see. Okay. What I'd like to do is talk a little bit about the programs on the CUSP website. There is a, let's see here. I'm trying to get this adjusted so that you can see. I'll just have to make sure I move it. It's one thing about using a blackboard or a whiteboard in a classroom. You don't have to worry about moving it around so that the students can see it. It's just permanently nailed to the wall. This isn't right. Okay. I'm going to show in CUSP on the website is a thing called labs. And these are MATLAB programs. So you need the MATLAB programming system to run them. But it has programs and it also has data files. So programs and data files. And there's a user manual that covers all the programs. And we're going to do the optimal power flow. And the reason I'm doing this is that I thought, well, I could have given you problems to run and solve on the MATLAB programs, but I'm not sure that all of you have access. If you're in academia, you probably do. Maybe professional, maybe you do as well. But in lieu of doing that, I will demonstrate them, which is perhaps just as well. But we've got two optimal power flows, OPF, one using what's called the, it uses quadratic programming, and that's an algorithm that's part of MATLAB, part of its optimization toolbox. And then it uses the so-called, we'll call it DC power flow, to model the transmission system. So the quadratic programming is very useful for us because you remember that our Lagrangian is always the sum of the cost functions. But if the cost functions are A1 plus B1 P1 plus C1 P1 squared, well, that's matches up to quadratic programming perfectly. So we use that, and quadratic programming, I just put a note here, it has quadratic objective linear constraints. And then our linear constraints are done with the DC power flow, which we know is linear. And this actually is used still widely. Maybe not as much as it was originally, but this was the way people modeled the power system to do the dispatch for the deregulated systems. And what we're going to learn is that in the deregulated systems, the generators send in bids, which are they say, here's the quadratic coefficients for my generator's cost function. They build that and send the coefficients. The ISO has the power system model, so they do the DC power flow model, and they can get a solution for this quite readily. Let me say that one of the reasons that the U.S. could go to this type of OPF model to do their it's really the auction that people bid into, and then it decides what generators are going to operate and what power output and so forth, and it's going to do transmission flow limits, and it's going to do contingency constraints, etc. Without the OPF in the simple form, at least, you couldn't do that. You could not have that type of model. You could not have that type of deregulated operation. So I always told my students that the deregulated operation was only possible because we developed workable OPF algorithms. And as I said, Jacques Carpentier started the whole thing back in the late 60s, early 1970s. To be honest with you, he formulated the problem and had some kinds of solutions, but they weren't that workable. And people proposed workable algorithms that really didn't work for years. And even yours truly, myself, we wrote an algorithm that was based on a very special, it wasn't quadratic programming, but it solved nonlinear cost functions using something called Danzig-Wolf. George Danzig was the guy that started the whole LP thing, and then this was Danzig-Wolf was a way of linearizing and then updating linear segments during the LP. And so we could do nonlinear cost functions with linear constraints. So we were doing this OPF back with that method back in the early 1970s. It worked, but at that point there was not that much demand for it, and people all wanted to solve the AC OPF, and I would say it took many more years to get to the AC. So OPF AC. So this is OPF. You can call this linear model for the so the AC OPF basically came down to two methods that I know of, and one of them is called incremental linear programming, and I will discuss this in a while. And the other one is called the interior point method. Now they're both covered, excuse me, they're both covered in the textbook. I am not sure, I think both of them are in use. The MATLAB, there is a MATLAB program I'm going to demonstrate that uses this incremental LP. One of my graduate students who now works at PJM, his name is Anthony Giacomoni, and when you see the code come up on the MATLAB window, you'll see his name. he needed a project for a class, and I said, let's do this. And so he did it, and then we took that and we expanded it, and then I expanded it and added certain kinds of constraints and so forth. So we will explain this one as well. So let's talk about the QP OPF with the DC power flow. And so the variables that are in there, so the variables are P1 to Pn, all the generator outputs, and I just keep them in megawatts. It makes everything simple when you're doing it that way. And then I'm going to. So then we have the B sub X matrix is part of the data that's in there. So they're not. It's in the algorithm, and then theta I up to theta, let's call it NB for number of buses. So there's the theta for each bus. Now this can get to be a very, very, very big model. I'm going to demonstrate later on solving the 100. There's an IEEE model of it's 118 buses, and in the CUSP website data, the data has that model, and it has a figure that we drew of that model. If you ever use the program PowerWorld, it also has that model. Incidentally, I just want to let me just give a little plug here for a friend of mine, Professor Tom Overby. He was at the University of Illinois. He's now at the University of Texas. And he wrote this program called PowerWorld. I recommend it very highly. You can get a free version. I think the free version goes up to models of up to 25 buses or something like that. And it has a picture of the power system, and the flows are represented by arrows moving. When I first used it, I wrote to Tom and I said, you could put reactive power on there as more arrows, different color, moving whatever direction. And he did. So it now has real power and reactive power. It shows voltage magnitudes. It has more innovative things in it. And it has a full OPF inside. And it originally had the DC OPF with quadratic programming. And then he actually also put in an AC OPF, and it'll solve great big multi-thousand bus systems. It's used all over the world, but you can get the 25 bus 20 version free. Do a search in Google on PowerWorld, and I think it's powerworld.com, but they're a corporation in Urbana, Illinois. That's where Tom was working at University of Illinois, and so they started the company down there, and I knew several of the people, including the president of that company. Very successful, small company, and people use this PowerWorld program. You can do power flows, optimal power flow, short circuit analysis. You can do some stability analysis. It is a very, very complete package. Although if you're doing engineering work, generally people like to use the product from Siemens / PTI, which is PSSE. If you're in the business and you haven't heard of PSSE, look it up, and you'll find out about it. If you're at a corporation, it's a wonderful it's a tool that's been around for 50 years or so. Lots and lots and lots of development. They have models for exciters and models for generators and models for wind turbines, and on and on and on. So it's a very, very complete engineering package. It's not free. It's cheap. It isn't cheap either, although you can get an academic version of PSSE. All right, so might as well give them equal PSSE from PTI. It's a division now of Siemens. It's in Schenectady, New York, which is where it was. I worked there for a while myself. Okay, so the DC one, it has the B matrix and so forth, and so they literally solve this equation. There's a set of equality constraints that says P1, P2, all the way to PNB, all the buses, that be they generator or load, equals B sub X matrix times theta 1 to theta NB, all the phase angles. Let's do this. Let's call this NG for all the generators, and they're buried in this vector. So this is a set of equality constraints, and you know that we build equality constraints. There's going to be a lambda that simply says that we have a vector of lambda 1 to lambda NB times the P vector. Let's see, no, I'm going to put it this way. B sub X times theta, and I'm just going to use vector notation, minus P. That's the vector of bus powers. And these have a very interesting nomenclature. These lambdas become, let's see, I think you should be able to see that, yeah, become the bus marginal cost. Or bus marginal price, BMP, bus marginal price. And every bus has a marginal price. Rather than one lambda for the whole system, we have a lambda for each bus, which is the cost of power. If you want to buy a megawatt of power at a bus, you pay the bus marginal price per megawatt if you just want to buy one. And that is the basis of the deregulated system. So anyway, that's this. Well, you understand that if I'm solving for thetas, if it's part of the model, then I can say I can have flow ij equals 1 over xij times theta I minus theta j, and I can say that's got to be less than or equal to flow ij max. So I can have a limit on every flow in the network. Now my models tend to do that. They have a flow, they have a max flow for every possible flow. And what we're gonna see then is that in addition, so the QP OPF linear model, sorry, again, sum of the C of P and it has the DC power flow, and it has Fij equals 1 over x theta I minus theta j less than or equal to, whoop, Fij max for each line. And then we could also have contingency limits. And what I want to put in there is I want to say Fij with F and M. And this represents line L. This is at line K out. And we know the expression for this with this line out is Fij line L equals Fij L0. Let me just put the 0, meaning the initial condition, plus line outage distribution factor times F and M0. Well, these in turn are functions of 1 over x theta I minus theta j, and this one is 1 over x theta n minus theta m. And so that's a contingency constraint. Now, I don't put all of these in because I could have, because L can go from 1 up to the number of lines, as well as K can go 1 up to the number of lines. And in this case, I should really say -1 because I don't look at the flow on L when L itself is out. Well, that's if the number of lines is 1,000 or let's say 2,000. 2,000 squared, right? 2,000 squared is about what, 4 million? So that's a huge number of constraints. So you don't put them all in. And what you do is you solve the base case, and then you solve, and then you do a contingency analysis. And you put the worst contingency overload into the quadratic program, and you solve. And you solve QP with worst overload. And then you do another contingency analysis. I used to call this iterative constraint search, and that's you're trying to find the most binding constraints without putting a million constraints, well, let's say, hundreds of thousands of constraints in at the same time. And when you put this worst one in, then you put the next one in, the next worst, you keep this one in, and you just keep adding them. And usually you don't get too many. My opinion, if you have a power system and you go to do a contingency analysis and outages on 25% of the lines are going to cause overloads on other lines, your system is not adequate. Your system is not designed to handle as much power as you're trying to push through it. And you can't really operate that way. It's usually a small number of outages that you have to worry about. One of the reasons being that if you correct for one outage and you correct one contingency constraint, you will eliminate a lot of other constraints because they're close to each other. If you have a lot of lines, for example, that are flowing in one direction, from, let's say, north to south, I always use the example of from Canada to the US because there are a lot of lines like that. Well, if a contingency on one of them causes a problem, you have to back down on the flow. that affects all the contingencies on all the lines that are coming from that region of Canada to the US. So it's not going to go to hundreds or thousands of lines. It's just going to be a few that are the binding constraints. You have to operate, remember again, the N-1 rule. It's a NERC rule, North American Electric Reliability Corporation, working with FERC here in the US, that says no single outage causes an overload. Okay, no single outage. And if you operate that way successfully, then you do have a single outage. It will, the result will be the system will still be within limits, and you won't have any more cascading. You may need to correct things. You may want to correct things at that point, but you won't have a disaster. You won't have one outage causing an overload, which causes another outage, and the domino effect, whatever you want to call it, cascading outages or domino effect. One causes the next, causes the next. You don't want that. So that's why we do the N-1 rule. And that's why they operate it that way. Now, this is the part that is very important. Keeping to the N-1 rule. There. Increases cost of delivery. I give you a very simple, dumb example. Here we are, and we have some hydro plants. Let's say we have some hydro units over here. And we have two transmission lines, and over here we have some steam units. Here's where the load is. That's a simple power system. I want to supply this load. Well, the hydro is probably going to bid into the auction much cheaper than the steam units, and we'd love to say that those two lines will always be there. Then we can buy almost all of our power from the hydro. Everything is great, it's cheap. But if we lose one of these lines, then the flow on the other line is double, assuming they're equal impedance, that it'll just double. And that might be way too much. We can't operate that way, because if we do, and we do have that contingency, then you're going to have a problem. You're gonna overload this line, and then you're gonna lose the connection completely. So what we have to do at this point is say, no, we're going to have to back down. No, literally, you have to back down so that if they both have P max on them, if that's the maximum flow, then all you can carry is P max over 2. Because if loss of one means that the other one will go right to its limit, that's okay. It can operate at the limit, but you don't want to operate over it. So this reduces the amount of power to just the maximum on one of them. And that means that maybe you have to supply some of the energy from the steam and not all of it from the hydro. So it's costing more. I can't get all the cheap energy I want because of the transmission limitations, but I have to operate that way. They have this rule so that we don't end up with an outage. All of this is lost, and because the transmission just simply won't allow that. It's obviously more complicated, but that's the way they operate. You worry about, an outage causing a low voltage. You don't want the system to go voltage collapse. So that's another thing that we worry about. Okay, so let's.
Excuse me, I have a question.
Yes.
There in that page, and you put the LODF, the line out distribution factor. In the lecture, in the video, there is this line sensitivity, the A factor is the same?
That's the same thing in the lecture. Where it's O, does it use A on the video?
Yeah, and it is, and it doesn't elaborate much about the A, but briefly it says line sensitivity or something like that.
I thought I'd gotten the A factor is the same as LODF.
Oh, okay, thank you.
What happened is we wrote the first edition, I think maybe even the second edition of the book, and then we also had D factors.
I haven't seen the D factor, no.
And D factor is the PTDF. And then along in the 1990s, with the deregulation and the economists, I mean, literally, this is true. The economists coming in from the outside brought with them a lot of desire. And I know this is true. If you look at economics papers and so forth, they are very, very rigorous mathematical people. And they said, let's call that the line outage distribution factor, the power transfer distribution factor. Well, let's face it; those are much better names because you know what they are. And so, in the third edition of the book, I tried to change all of this to PTDF and all of the A factors, and there may be a few of them, lingering around someplace. I'm sorry about that. That should have been changed to LODF. Okay?
Thank you.
Yes, sir. Thank you for that. That's a good question. All right. Let me demonstrate. I'm going to demonstrate the QP algorithm on MATLAB, and we'll first show you. Let's see. We'll do this, and then I'll come back to this sheet. So QP OPF with DC power flow. So we'll do a base dispatch, and then we will do a dispatch with line outages. Now I'm going to use the 6-bus model, and I had Jairam put, okay, here we're going to go back to, let's see, I don't need to turn this camera off as long as I'm doing, yeah, right. I guess, I'm sorry, I did this wrong. I've got to open up, there we go. And we will go to share and boom. And you have this file is on the system. Let's see, can I do this? No, I can't. Oh, wait, I can do fit page. So you have this file. It's a PDF file. That's the one that I'm displaying. So you may want to grab that, have it available, or print it out for yourself while we're talking, because I'm going to refer to this model, and I have it on a piece of paper as well, so that I can mark up the paper. So what I'm going to do is the name of the program that I'm going to run, incidentally, is called let's see, I'm not sharing. So you should be able to see, right? Yeah, we're still on. So I abbreviated this as DCOPF_QP. Okay, that's the program, and I'm going to yeah, we're going to bring that up, which is here. There it is. Okay, this is the MATLAB programming tool, and let me tell you, this is the program. You get all of these programs on the CUSP website. They're part of the so-called labs, and there's two sets of OPF programs. One is this DCOPF QP. When I started out, I used to use MATLAB files as the data files, and editing them, it became a nightmare. Editing in MATLAB, when you're editing data files, it won't keep things in columns for you. At least the MATLAB editor won't do that for you. And so I adopted a different system, and I'm going to show you that. This is the 6-bus data. All of the data is in Excel spreadsheets. MATLAB can read Excel spreadsheets, and editing an Excel spreadsheet is just easy. You go to the, I'm going to change this value later on, so I just come and I change the value, and then I just have to save it, and then the program can read it. So I keep it open. So these are all the control variables. Here's the bus data for the 6-bus system. There's 6 buses. Here's the loads.
Professor, excuse me, you are not showing the screen.
It doesn't come up. Let's see here. Share. Well, there's got to be a, oh, here. Sorry. Let's go back. Now you should see it. Here is the, yeah, this is I use sheets. They call them worksheets. So there's parameters, bus data, generator data, branch data, area names, which are not required in this one, and generator cost data. We have extra data. Don't worry about that. That's just stuff that was left over. I stuck it on this extra sheet. MATLAB starts up and it reads all these sheets. So here's the bus data. There are 6 buses. See, bus number. All the data is labeled, and you can easily edit one, or you can edit one and paste it into many of them. So here's the voltage min and max for the line. Here's the loads on the buses. Here's the generator data, the power, the Q min and max, the voltage that it's going to operate at, and so forth, the P max and P min, very important for optimal power flow. Here's the branch data from bus to bus, RX, charging capacitance, and so forth. Rate is just rating. I don't know how that thing, did somebody see that? Did you guys see that little red thing? Anyway, area numbers, area names, which are not important. Here's the generator cost data. There up here is ABC. There's the values. There's even some shutdown costs and so forth. And these are just numbered one for 1, 2, 3. Okay, so we read. Let's see what I want to do now. You should see that data applies to this 6-bus system, and now I've got the MATLAB case up. If you can't see something, tell me. I should, although not right now, it shows this. Let's go back. Am I showing that? Yeah, I am. Share. Are you seeing the MATLAB window?
No, we are seeing the Excel
You're
screen.
still seeing Excel. All right, I'm sorry. I will stop this and we will go, whoop. We will go to share and we will go back to MATLAB, like there. That should be a, that should,
Correct.
yeah.
we see
now you see this program. Here's the MATLAB code over here. And this is just the program that's reading data from this data input. Now what happens here is when I start it, this, whoa, this thing doesn't seem to like that. Okay. So I'm going to start and tell it to go. It gives me the spreadsheets of all the data that I have: 6 bus, 12 bus, 118, and something called the RTS, stands for Reliability Test System. It's an IEEE case. And it's now reading the data. It just reads and starts and runs. And then we will have to go through and kind of explain all of this when it runs. It takes a while to read it off of the spreadsheet. I should have had a little thing that said, hang in there, I'm still, wait a minute, remove this window away from the shared application. I have no idea what that's all about. There it is, it ran. So let's come back up here. So when it runs, here's, look at that. It's still calling this the A factor. It should have called it LODF. And so the program still called it A factor, but that's the same. Line goes out, monitored line. It displays these factors. Here's the PTDF factor, comes up over here. And when it does the first QP solution, it finds that there are flow limits. Now the flow limits are on lines 2 to 4, and 3 to 6. 2 lines that are coming up to their limit of 60 megawatts, and so it does a dispatch, and the total cost, let me 4158.2. I'm just going to write that down. So base dispatch 4158.2. That's dollars per hour. That's the cost to operate with those 2 limits operating, with the two limits giving us the dispatch, and that's a base dispatch. It will always obey these limits. Now here, for example, is the limits down here, and you can see this line 2 to 4. I'll just highlight it. Whoop, there we go. 2 to 4 says that the limit is at 100%, 60. It adjusts the generation to get that limit, that line, and the same thing down here for this line. Now I want to show you something else too. There are bus lambdas. Notice that they aren't too different, but they are different. So these are the so-called bus marginal costs, or bus lambda, for each bus on the system. And then for constraints, we have there's going to be a lambda. It would be the letter mu, but I call it line lambda, meaning the incremental costs. And what these lambdas are down here are the amount of change in the total operating cost if you were to relax the limit on the constraint. So it's sort of a measure of how much that constraint, and you can see that this one has a much bigger effect than this one, almost double the effect down here. So on the line from 3 to 6, if you changed its limit roughly, let's say by 10 megawatts, well, you'd get something in the neighborhood of 16 better cost. The cost would go down by 16. Whereas the other constraint, if you changed it by 10 up here, you'd only get 8. So those are measures. Those are very, very important to know those kinds of constraints. If you're planning a new system and you have some new lines in and you do a dispatch, it's going to tell you a little bit about the economics of those lines. If they're limiting, that's the case. Now, what we're going to discover next is we're going to go back and we're going to change the data. I think I'll show you how I do it. This MATLAB does not like this. There. Is it happy now? No, it's not happy. Anyway, let me go back. Let's take it off, and I will go back, and we will just look at this the spreadsheet. And here is the page called the parameters page. And what I'm going to do is I'm going to just change this to 1. So this is why I like using spreadsheets. I can edit and it's all the variables have labels next to them as to what they are for, and that's in the spreadsheet code right now, or that's the program. And if I want to make that available on the on the directory or the file, I just save it. So now that's a change. And so stop sharing. Oh. And we'll go back to MATLAB. Now I should get both windows. There we go. So now I'm going to run it again. And as soon as I run it, you notice the first command is to clear, and that clears this workspace over here. And we're going to go back to the same 6-bus case file, and we're going to run it. And you can see that we are now reading the case file again, but this time we're going to solve with constraints, with contingency constraints. And it's interesting to watch this iterative constraint search. So here's all the data, all the factors and things like that. And then it says it runs a QP, it runs a successful QP solution. And it does the first contingency analysis. It says if you drop line 1 to 4, that's one of the ones that was at limit, then line 2 to 4 overloads. And it goes up to 95. Now the contingency limits are higher than the regular limits. That's common. It simply says I can have a contingency that causes an overload on something that's higher than its normal rating. Sometimes they call this the emergency rating, and I will let the line heat up while I'm correcting the problem. I got to get it corrected, but I can let it go up higher. So we're going to let it go higher up to 90. And then it runs and it says it does a QP and it says it does another contingency limit. And it says if you drop 3 to 6, that's just a flow limit. And so now I've got a flow limit on 3 to 6 and I've got an active contingency constraint at 90 megawatts. And I come to the solution and I'm going to write this down. The cost is $42.67.2 per hour. Well, before it was $41.58. It's not a big difference, but the cost of operation went up because of this contingency constraint. Again, here are the bus lambdas here, and we now have we have one contingency constraint, one regular constraint, and then down here, I got to put this back like that, and down here, I'm having a great deal of fun because this. Okay, down here at the bottom of the screen is the contingency constraint. And it says that if I lose line 1 to 4, line 2 to 4 goes to 90. That's its contingency limit. And look at the value of lambda. That contingency constraint has a lambda associated with it that's 35. Which says that if I moved the contingency limit by 10 megawatts, I'd get 350 less cost, approximately. I'd get a much lower cost. So these are relatively the sensitivities, and typically the contingency constraints are much more sensitive. So that's an example of what you can do. Now, you can run, I think given the time, I think it's best if we go and we do the AC cases. And what I'm going to have to do here.
Professor, before we go to the AC, I have a question on the DC.
Sure.
It won't calculate transmission cost and losses.
It won't calculate losses. There's no losses in the network, no. There are ways to make it work. The Électricité de France back in the 60s, 50s, 60s, 70s had some very, very, very good work going on, and I remember reading a paper at the time where they would do a DC power flow, and then they would approximate the losses and put small loads at the end of every line. And that would be the losses. These loads, these extra loads would add power that they could, and they could make that model do something with losses. That was never widely adopted by the industry. Most of the, for the most part, because it still didn't really deliver anything to do with voltage magnitude, reactive power, all those. Did somebody fall over, or their desk? Whatever happened there? Somebody's microphone. Anyway, I'm joking around. Anyway, the U.S., at least within the U.S. and eventually within the Europeans also, the goal was to do this with AC power flow solutions. 1967, we had the real breakthrough. Bill Tinney and his crew from Bonneville Power showed us how to do the Newton power flow with what were called sparsity programming techniques. This was a huge breakthrough. And because it allowed us to solve very large cases without having great big full matrices. And that breakthrough allowed eventually, the same sparsity techniques allowed us to do AC power flow coupled to an AC OPF. So that's what we're going to do. We're going to do next. And what I'm going to do is, did that answer your question there, Gustavo? I think that was you.
Yes, very much. Thank you.
Okay. Yeah. Now, I guess right now you're looking at my hand, right? So, so let's talk about the AC OPF. What we do there is it runs on what I call incremental LP. Take this. Here's a window, and we had this problem the other day where we were looking at elliptical functions, and that's the objective function, and they get larger and larger. And let's say you're trying to optimize this, and you've got a series of limits. Maybe you've got, that's a limit. You've got a linear constraint, and then maybe another linear constraint, and so forth. And then you've got the zeros. So within this this boundary that I'm trying to highlight here now, you start out someplace, and let's say we start out right here. And what we do, when they say, okay, if I look at the whole thing, it's very nonlinear, and I can't really linearize it. But if I draw a small window around here, like that, and I say this is x2 and this is x1, and now I say, well, these are the limits that you can in here with these. That's as much as room as you. So now I've got an LP, and let's look at it on a scale down here. We've got this thing, and I've got something that's running like this, and I'm operating there. Well, I'm just going to linearize it, and I just take the derivatives, and I get a straight line that's tangent right there, and I say make the function linear. And it's as if the function looks like this. Well, I can solve an LP. Well, if you're maximizing, you're going to go to that point there. So that's up here. And then the next one, you come back and you put a window around this one. See, this is why it's incremental. And so now I'm gonna solve that one, and I get that window is going to look like this. And I'm looking at, and maybe the slope is slightly different, and it's going to drive it over here. It won't always be that way, because if I solve at this point and I put a window, now this window has the objective functions that let's say are like this, but then I have this linear constraint running right through it. So now I can't go to this corner. I just go up here. That's as best I can do. So as long as I have linear constraints, and I have these windows, so every time I pick a new window, I relinearize the objective function. Do an LP, and relinearize. Well, the linearization, it turns out, is done with the Jacobian matrix of the Newton power flow. So you solve for the optimum, and then you run a power flow. Now you have a new point to start with, and then you put the window around the point, and there's techniques for expanding and contracting the size of the window. If the linearization doesn't look too good, well, you change the linearization. and by clamping the window down, you don't let it move so far, and you don't want to let it move. You don't want to open the window too much, because then you know that if we move, your linearization is not too good. If you make it really small, it's very good, but it'll take a lot of steps. So there's a lot of adjustment and a lot of kind of heuristics that you do, and that's what this algorithm does. And it will solve with line limits. It will also solve with voltage magnitudes, because the voltage magnitude is already a variable in this LP. And so we can solve, and you keep solving the Newton power flow, Newton power flow, Newton power flow, and then you iterate that with the LP until you get to the optimum. And that works very, very well. So let me demonstrate. Now, what I'm going to have to do here is, okay, I'm going to have to go to a different directory, and we're going to go to AC power flow and run AC LPOPF. And you're not seeing this until I bring it up on the screen, but I'm going to have to go to the spreadsheet and close it. Let me come back to okay. And there we go. I'll start out with no contingency constraints, contingency limit checking, and we'll just do the AC solution. So now I should be able to show you MATLAB. There we go. Okay, now I'm going to run this case, and it says 6-bus case like this. Now it's reading the case, and it's reading all of the data again, and it's going to solve the AC Newton power flow. We're going to see a lot more output coming out here. I'm going to just run the AC case. You can, and here my student that did this originally, he put some nice graphs in, because this is an iterative process. Unlike the QP, when it solves, it's done, unless you change the constraints. This one, so the objective function starts and it converges like this. And once it's converged, it's there. And he put control variable error. You can see the logarithmic scale. And then it has objective function value error. And I'm not sure what he means by error there, but this is the objective function. So these are, I'm gonna take them out, but that's a nice thing to show the progress. We'll go way back up. In the beginning, it runs a base power flow. And there's the power flow. Here's the iterative solution of the Newton power flow. Here's the generation. There's one bus that's at its maximum voltage. These are the flows. And notice now we get voltage, phase angle, P, Q, P and Q on every line, and so forth. And we get a summary of voltages down here at the bottom, and any overloads. There's a P flow is 90.9. So it did a constraint on one flow. And now what does it do? It comes back and it resolves the LP again. It solves the LP. Let's come back here and show, where's this? And that's the iterative. There's our cost. And it started, and now it's going to solve the LP. So here it says run LP. And when it's done, it gives you the results, and it then runs power flow. The results are the power, P gen, it's adjusting, and any voltages it may adjust. These are the voltages over here on the bus, and it solves the power flow again. And it says we're going to run the power flow at the new point, and that's the same, virtually the same result. We've got this flow much closer to its limit now, and then it runs another LP, and that's the result of the LP. Then it runs the power flow at the new LP. So it just does this over and over again. So you have to have a very fast algorithm, but the cost, we saw the graph, and it's just getting less and less. The cost is going toward the optimum, and eventually, let's see, someplace in here. What I'm trying to find are the bus. I bet they're, see, I'm missing a whole bunch of data. Here's the lambda for the buses. And they're much different. They're much more widely spread out than they would be for the QP linear power flow case. The lambda for lambda P. Now this is the true bus marginal cost because it's done on an AC power flow. Interestingly, it has lambda for the Q of the bus. And what this says is that at this bus, let's do it at a load bus. At this load bus, if I want to buy 1 more megawatts, I pay $14. If I want another megavar, there's a cost. Now, why would there be a cost for megavars? Well, as you end up pushing more megavars through the system, losses are going to go up, both real and reactive, so the generators are going to have to change, and it's going to cost you. Interestingly, however, sometimes that lambda is negative, and it says, listen, it says if you'll raise your Q consumption at that bus, it lowers the cost. So effectively, I'll pay you to do that. That's what that's telling you. There are instances where the lambda for the bus itself can be 0 or negative. Very funny conditions that you get sometimes in these dispatches. But there's the lambda for the bus. Now, in the book, there's a very long, detailed analysis of this lambda P variable, and there's an explanation. It has to do with the generation at the reference bus, the cost, plus incremental losses on the network, plus the sensitivity of line flows and so forth. And there is a part of that chapter uses this LP, and then shows you that the calculation does indeed give you a value very close to what the program got. I should put that the other way. The program thankfully got a number that's very close to the theoretical, what you're supposed to get. So that's not always the case. And it just iterates and iterates until it gets to a solution, until it converges. And we kind of over-converged this. We got to so many iterations with just a little bit of change. It's okay, that's enough. But that's the AC case. It keeps running AC power flows. Now, the fact is, it's not. It can use the previous power flow, so it doesn't. You notice this one, it didn't even have to change. It didn't change much, so it's not gonna. Let's see if the one ahead of it. Yeah, it took 2 iterations. That's very quick. Very quick. It's pretty close to the optimum. We're adjusting just a little bit the power flow. The Newton power flow just iterates a couple of iterations and it's there. So that's an AC OPF. Obviously, commercial AC OPFs use techniques that are very, very sophisticated, built into CPlex. If we remember our old friend CPlex optimization to do the unit commitment. So that's the ACOPF, the secret of dispatching the power system. Now you've seen the ACOPF, it takes many iterations to solve, and so it's a longer running affair than the QP or with the DC transmission system. And that's why it is often the preferred way of doing dispatching. But the ACOPF is still very, very, very important. For example, if one of the voltages on the load buses under a contingency is low, the OPF can figure out how to adjust that. If it has some variable Q sources like static bar compensators, it can adjust those and tell you what to do. It's extremely powerful. It was the secret. Either the DC OPF or the AC is the secret behind being able to do the auction of deregulated system, which is what our topic will be later this afternoon. Okay, so let me stop sharing here and get, now let's see, I should be able to find, no, because I don't have this opened. There it is. I'm sorry, I did have it open. So we're now going to look at the control of generation. And I will, let's see. I need to post a problem for you. I need to post a problem. I will get that problem posted here in about 10 minutes. So you'll be watching the video first, and then I will have Jairam post that. It'll be available, a PDF file that you can read and do a simple AC, not AC. I'm going to talk about control of generation. We're going to do a situation where we have a power system and we lose a generator. Now that's the most traumatic event. If you're operating and you have an 800 megawatt generator, for example, and you lose it, you lose the generation. Why? Are you seeing the screen or my hand right now? You should be seeing this, the schedule, right?
Yes, sir.
Okay, I'm seeing the display with my hand, and I'm thinking that's going out. Well, it's not. Okay, if you lose an 800 megawatt generator, what's going to happen on the power system is suddenly you've lost some of the input, and so the load is greater than the generation, and it literally starts borrowing energy from the rotating mass of all the generators, and that slows them down. And so as they slow down, the frequency drops, and if you lose a generator, that frequency drops fairly fast. And you have governors that take over and move the generator. So we're going to have you do a problem which says, okay, I lost a generator. What frequency does it reach? And what does the interchange look like between areas and things like that? That's the key to control of generation. The frequency provides an virtually instantaneous signal to all the generators that there's something wrong. If you lose a large generator in Florida, you will see the effect all over the eastern United States. And all the generators in the eastern United States will pick up a little bit, but that little bit over hundreds of generators will make up for that loss. And then it's the job, let's say it's Florida Power and Light, it's Florida Power and Light's job to bring up more generation and get their system back in balance, but the whole system helps. That's the idea of it, and it makes the drop in frequency manageable. If you're operating a power system on an island, one of the first jobs I ever worked on when I was a young squirt right out of my master's program was a project for the Puerto Rico Water Resources Authority. I don't know if that's the same name, but there's the island of Puerto Rico, and it doesn't have lines, it didn't then anyway, to anybody else. It didn't have any big lines to the US or to any of the other Caribbean countries, or islands, let's say. So you lose a large generator on Puerto Rico, you've got a bigger problem than you do if you're in the continental US. And they need to have special controls and so forth. If they lose a generator and the frequency starts to drop, they need to drop load. So there is a thing called low frequency load shedding that they would instigate. So we will start that, and within about I'll say within by 11:30. I will have that problem on a PDF, and I will have Jairam posted for you. Okay, so we will see you at 11:30. I'm just going to leave this this up for the time being here. Okay, and we will see all of you. You will. I'll say something so you know where to go and get it. But I will have email the problem to Jairam for you to look at. So see you then, 11:30. Okay, I'm live again, and I'm just going to give you a little intro to the problem and a little hint as to the way that we do it. One of the things that you need to know. You will discover from the lecture, the video, that generators have what's called a governor droop. Function, and it says that here is the, let's just put a 1 next to it, and it says if the generator is operating at a certain frequency and a certain power, and then the generator changes its power output, what happens to the frequency, or vice versa. If the frequency changes, where does the generator go? That's really what's going to happen. As you may recall, here's the generator, here's the turbine, and of course this is causing the generator to spin. And here's the power output P, and we're measuring frequency omega. We're measuring that, and we're bringing that back, and we're going to change the steam. We're going to change the steam input to the turbine, and there's a slope to this, so that if the frequency changes, let's say the frequency goes down, which is a case that's typical if you lose a generator. So the frequency goes down, delta F. So in this example, delta F is negative. It went down like this. Well, then the real power goes up. The generator power goes to 2, and this is F2. So frequency goes F1 to F2, and which is lower. So delta F is negative. P goes from P1 to P2, which is higher. So delta P is positive. And what we say there's the slope of this is expressed as capital R equals delta F over delta P, where this is expressed as a percent frequency change divided by per unit power change. And we like to work everything in percents and per unit, because then we don't have to worry about the sizes of units until the very end of the problem. Now, the problem statement doesn't show it, but we always express R as a positive number. Okay, but it should be, that positive number is equal to the negative of the frequency change divided by the delta P. Okay, so that you get a positive number out of it instead of a negative number, because delta F is actually negative, delta P is positive. So you put a minus sign there. That is missing. It's not really missing, but I should have said the absolute value of the governor constant. That's kind of a silly way to do it. Just remember that in the problem statement, and here's the problem, that this should have a minus sign right here. Okay, and then you can do all of the problems. And what we're going to be looking for is the delta F. We're going to use this. We're going to use this in calculating what happens when we lose a generator. So I'm going to sign off again now, and you have you have roughly, so what is, I said 11:30, I'm a little late, but it's about 12. So I'm going to give you till 1, maybe 1:15 to look at this problem, control of generation, and then we will jump into interchange, pooling, brokers, and auctions, the last topic that we're going to cover this week. And we'll do some sort of problem for that as well. Okay, so this is the problem. You will be able to get that as soon as, let's see, Jairam, have you posted it yet? I'm gonna look. Usually Jairam is very, very, very good about posting for class. He did. See, he is Johnny on the spot here. Excellent. Are there any files also? Could you please remind them that maybe sometime in the afternoon? Yeah, I want to remind you, and I'm supposed to remind you later on, that once the class is over, all these files, because they have some copyrighted material, will be removed from the website. There will still be some stuff on the videos of the course, but not these files. And I'm going to answer him and say, okay. So, that's the problem. You can get that now. He says that's been posted for you. And I am going to, pardon me, I'll be back here a second. I'm going to come back after your lunch break to, let's say, 1:15 to 1:30. Okay, we'll give you time to work on that problem. Okay, people, we have this problem on that we sent to you on control of generation, and it's right here on the screen. And I noted that the R figure here is equal to delta F over delta P, where this is percent frequency change divided by per unit power change. And I noted that there should be a minus sign implicit in that. We usually quote them. You can see here that we are quoting it as a positive number. But the implication is that either delta F or delta P is negative and the other positive. So if the frequency goes up, delta F is a positive number and then delta P is negative. But if R is going to be positive and one of those two, either numerator or denominator, is a negative number, and we have to stick a minus sign out in the front to get a positive number up here. But that's key to understanding this problem. Now, what I'm going to do is kind of go through the solution to this problem. This is this was a test problem a number of years ago, and so I'm gonna talk about if you have two generating units. Okay, so here's one, and let's say it has a very steep droop curve, and here's another one with a very shallow curve. This is probably a small generator. This is a large one. In any event, here's the F0, and for some reason the frequency goes down. Let's say we lost a generator, so the frequency goes down, it drops, and obviously the scale on here is way off. But you'll notice here it just called this unit number 1 and this is 2. So here's delta P1 and here's delta P2. Wow. So you can see that you get for the same change in frequency, you get a small delta P on this one and a large one on this one for the governor's response for those two generators. Now, what we know is that if we have two generators on the system, and they don't have to be at the same bus, they're spread out any place. And here's a generator down here. No, let's say this is a load bus, and there's some load, and so suddenly I'm going to add another load. Let's say I have another load down here, and I'm going to show a breaker, a switch. So here's another load, and so I'm going to close that switch, and that means that the frequency is going to drop. More load means that the balance between load and generation is now is more load than generation. More load than generation will result in the system slowing down because you're stealing rotating kinetic energy from the generator, from the turbine generator, because you put more load on, and so it slows down, and as it slows down, the frequency drops. Not a lot, not much. It may look dramatic, but it's a small amount. But so we get this situation where the frequency drops. Now, you're going to get, let's say this is 1 and this is 2. So you're going to get delta P1 and you're going to get delta P2. So in this case, delta F is negative because it went down, and each delta P is a positive, right? Okay, positive. Now, let's say the delta load, we're just going to say delta P load down here. So eventually it will reach a state where when I drop the frequency, but I get more power out, and the increase in power out summed over all the generators equals the new load, then it's balanced again. Then the frequency doesn't have to keep dropping anymore. So what we want to say in that case, so we're saying is that the delta P1 and delta P2 add up to the change in load. Okay, so here's the key: delta P1 plus delta P2 equals delta P load. Okay, so we need to and in this case the load was an increase, so this was positive, so these had better be positive. We better get more generation to solve more load, and therefore we're adding these together. But we know from our formula R equals minus delta F over delta P. Therefore, I can say the delta P of the generator is minus delta F over R. So now I'm gonna put in here, instead of delta P1, I'm gonna write minus delta F over R1 plus minus delta F over R2 is equal to delta P load, which again is a positive number. Therefore, I can take the delta F out and say minus 1 over R1 minus 1 over R2 is equal to delta P load. And then I can solve it. Delta F is equal to delta P load divided by minus 1 over R1 minus 1 over R2. So that's the idea of these governors on the system. And I'm going to go through the problem and do the numbers, but you notice I've got minus ones in the denominator. Therefore, this is going to be a negative number. That's going to be a negative number. So as the frequency dropped, the generators went up until the increase in generation equaled the change in load. An increase in load is the same thing as a drop as you drop a generator, and so but the point, of course, is that if you have hundreds of generators, like the big interconnections, if we have hundreds of generators, there's a lot of these terms. And so the amount of frequency change causes a little bit of change on all the generators, and that results in a number that's large enough to equal the lost generation. Of course, that lost generator is no longer part of it. Okay, now let's go back to our problem, the numerical example here, the problem itself. In this problem, this generator, this load is lost. So this is a case where we lose a load. We don't gain a load, we lose it. It's switched out. Now, what should we know that happens? Suddenly the load is reduced by quite a bit. If that's the case, we have more generation than the load is on the system. Therefore, the generators will start to speed up. What is happening they will start to speed up, and the frequency goes up. So if we go back to this curve, if the frequency goes up, the frequency goes up in this direction, well, then the generation comes down. Okay, so that's reasonable. It goes up because there's more energy from all of the prime movers, from all the steam turbines, gas turbines, hydro turbines. There's more energy going into all that rotating mass than load is on the system, and therefore it's going to start to speed it up a little bit. And therefore the governor sees a speed up and reduces the prime mover power that much over all the systems until the speed is now higher, and the generation equals whatever load is still on the system. Okay, now we said that this guy is generating 200, he's generating 300. The load here is 400. Well, that's what? That's 500 megawatts. So he's exporting 100 megawatts here. And G3 is at 350, and this guy is at 250, which is what? That's 600, and load 2 is 400. These are the initial conditions, and this load is initially 300. So I have 700 megawatts of load, 600 of generation, and 100 of interchange, 100 of megawatts coming in. Now, you in the video we talked about the fact that knowing the delta F and measuring the net interchange, in this case it's just how much power is going in and out of the area. There's a very simple logic rule that'll tell you whether the problem was in this area or this area after the event. And the event is that we lose 300. So let's see what the conditions are immediately after the loss of that load. And to do that, I'm just gonna apply the same logic that I did before. I'm gonna say, well, the delta P load on bus 3 is equal to minus 3.0 per unit. It loses 3, and these are all the base of the system is 100 megawatts, so it's 3 per unit. I've lost 3. It's negative. So it says that the change in load minus 3.0 is equal to, and we just do this, 1 over R1 plus 1 over R2, 1 over R3, 1 over R4. Remember, we have to have minus signs in there, times delta F. Well, this is minus 1 over 0.05 plus minus 1 over 0.1. plus minus 1 over 0.15 plus minus 1 over 0.2 delta F. This is equal to minus 20 plus 10 plus 66667 plus 5 delta F. And when you do this, this number comes out minus 41.667. And so delta F equals 0.072. And then we said that's a percent. So therefore, the F new, the new frequency is equal to 60 times, it's really 1 plus 0.072 to get a, because this is a percent change. And the 60, it's a percent of that. This comes out to be, pardon me, this divided by 100. This is a percent, so we're going to divide it by 100 to get an actual fraction. And this comes out to be 60.0432, assuming it was originally at 60. I assume it was originally at 60. So the change is this 0432. It's very small. It's very small. We're looking at very, very small changes in frequency. So then if I want to say, okay, if that's the delta, delta F, well, this is the delta F. Then the delta P1 is equal to minus 0.072. Remember, remember our formula up here again. R equals minus delta F over delta P. So minus the delta F divided by, and then this is divided by R1. And we get minus 1.44. Okay, so we lose generation, frequency goes up, the generators have to drop. And the answers are minus 144 minus 0.72 delta P3 equals minus 0.48. Delta P4 is minus 0.36. So P1 new the new values. Okay, so originally they were at 2 equals 2.0, and then minus 1.44 leaves us with 56 at 0.56. P2, these are the new values, was 300 minus 0.72, and that comes out to be 2.28. P3 is, where's P3? 350 minus 0.48 equals 3.02. And P4 equals 250 minus 250. I got to divide by 100. I'm sorry. These are per unit numbers. Per unit was divide by 100 because these are all per unit. So this is 0.25 minus 0.36 equals 2.14. So in megawatts, then we got to multiply back by 100. And so then you fill that table in. So the table is an interesting, the reason I did that. Here's G1, G2, G3, G4. And I said the new values, and this is area, 1 and 2. This is 56, 228, and then 302 and 214. Okay, and these are not interesting to us. Frequency F goes from 60.0432, and it's the same frequency in both areas. We always assume that the frequency is the same throughout the system. That's not an instantaneous effect, but is very, very fast. Now the final tie flow. The area 1 generation is 56 plus 228, which is 284. The load is 400. So the tie flow has to be going 116 megawatts from area 2 to area 1. So the tie flow and notice that the tie flow turned around and went the other way. And if we go back to the original problem, we had 100 megawatts flowing this way. Now you lost this load here, means you've got a tremendous amount of generation that's greater than the load over here. And unit number 1, because it has such a small value of R, he takes a big change in generation, so he drops a lot. And so after the event, this flow turns around and goes the other way. Just an interesting side note on that problem. Now, just to summarize a lot of this, what AGC does. So on the system, we have an event, such as loss of a generator. That's a big event. We have a change in load, and usually these are small over a certain period. Even during a high rise in power in the morning, everything's coming on. That's still relatively small on a control basis, whereas the loss of generation is a huge change. You get one of these, and the first thing that happens is you get governor action. So you get a delta F, and that results in a delta P on all generation, either up or down, depending on whether delta P was positive or negative. And we've gone through the reasons for it being positive or negative. So now at this point, then generation is no longer at economic set point. That's one thing. 2, frequency is no longer at, or I should say near, 60 hertz for a US system. If you're in South America someplace or Europe, it's 50 hertz. So the system, so we don't want either of these to hang on. And so the AGC, which is called a supplemental control. In other words, the primary control here is this one, the governors. they take action first. And now this AGC comes along as a supplement and says, okay, we've had this event, no longer at economics, no longer at the right frequency. And so wherever the area is, it will, in this case, it's up to this area to reduce its generation because he's no longer got 300 megawatts. He has to drop these generators by some combined amount of 300, and then this will return to normal over here. And so this happens within the area where the cause started, in which case for us it's area 2. And it needs to recalculate economics. There's no unit commitment change, but the economic generation, and then try to move generation to the economics, to the economic set point. I should call it the new economic set point, and try to move frequency back to 60 hertz. And so that's the job of the automatic generation control system. So this action takes place, and then over the next several minutes or hour, it's making these adjustments to get the system back to its new operating point where things are at economics and the frequency is at 60. And that's the essence of automatic generation control. You may have heard there was an older term, and the term was tossed out by the IEEE. The IEEE, it used to be called load frequency control, LFC. And finally somebody said, we're not controlling load, we're controlling generation. And that was one of those moments, I'm assuming, at some subcommittee meeting at the IEEE. And everybody looked around the room and said, yeah, but we've always called it LFC. And the other side said, yes, but we should do it. We should call it what it is. And so they renamed it Automatic Generation Control, AGC. And that was changed, I don't know, many, many years ago. So, but you may still hear people talking from time to time about LFC, load frequency control. It's not load frequency control. It's AGC. And that's the purpose of AGC. So what I think I'm going to do now, is get right into the next problem. And then I'm going to let you go off and do the videos on the final video of the week here, which is module 15, pooling brokers and auctions. So I'm gonna okay, now I can do it. We're going to let you get started on this right away. We're going to go through this power markets problem. It's a long problem. The problem takes 4 pages, and there's a lot of reading to it. So let's just go through it. You were asked to analyze a bilateral transaction versus a market auction for a 3-bus system below. All right, let me switch back to the screen here. If I end up talking and you can't see what I'm talking about, yell at me, please. I think we're back on this thing. So what's a bilateral transaction and what is a market? A bilateral transaction, there's a seller, it's a generator, let's say, and a buyer, which is a bus with a load on it. And they get on the phone and they just negotiate a price. And the buyer says, I need to buy so many megawatts for so many hours. And the seller says, I can do that. I can sell that to you for this price. And the buyer said, oh, that's a good price. I'll take it. One of the interesting things is that about the power industry is that the word of a power system operator or trader that they will buy or that they will sell at a certain price, I presume they probably confirm it by electronic messaging, email. It's confirmed somehow, but they don't. That's considered binding as a contract. And they probably have an electronic means of verifying it. Yes, I agreed to that. And, you know, that's a binding contract. So the seller has to sell that much power and can only charge what their agreed price was, and the buyer agrees to buy it. And I'm sure there are ways of getting out of the contract with penalties, blah, blah, blah. But let's just stop there. But that's considered a contract. They set up a contract verbally. And if it starts the next hour, the seller raises his generation and he turns on whatever he's trying to supply the load to, and he buys that power for over the period of time agreed. So that is a bilateral transaction. Now, of course, the market auction, I've got generators like this all over the system. And I got this guy down here who says, well, I want to buy power, and goes to the market and says, I would like to buy so many megawatts, and I'm willing to pay up to this amount of money. Maybe he's hoping that somebody will come in at a lower price, but he's willing to pay so much money, and he puts that bid into the market. So these guys are submitting bids to sell. He is submitting bid to buy. Bid to buy. Now that's what an auction is. But when we think of an auction, if you've watched any, I'm trying to think of shows on TV where things are being auctioned, and once in a while they will show you an auction such as takes place in like major city for works of art. Auctions. The purpose of an auction. Why do an auction? They're used when a price needs to be established. I have a price list. I don't want to use that word, price list. I have a rare work of art, a painting. How much is it worth? Well, I can get estimates. And if you ever watch the Antiques Roadshow, I happen to see it once in a while because my wife loves it. And so she's watching Antiques Roadshow on the TV when I come into the kitchen, and I hear that the guy always says, if this item were brought to an auction, I would estimate it would bring so much, but that's an expert. But he can't look it up in a catalog. The only time you can look something up in a catalog is if it's being bought and sold over and over again. And then the market knows what the price is, and it's on a web page or it's in a catalog, and you just look it up. But if it's a rare item, if it's a painting that's hundreds of years old by a master, they don't know what price it will bring, because the last time it was sold was 368 years ago or something. So you need to establish a price, and the item comes up. Now in that kind of an auction, we say you're trying to sell something. So there's a single item being sold and there's many buyers. In this one here, we're reversing that, and there's many sellers and one buyer, and they put bids to sell, bids to buy, and they try to match it up. And we talk in the chapter and in the video about the procedures that they go through to match these things up. Anyway, this problem then, if we come back to this, the green load at bus 2. So here's this green load, is trying to buy 500 megawatts, would like to buy from the hydro plant. Okay, so I said he's a green load. This is a company that brags to its customers. So this is let's say this is a small municipality, and they say we buy from green suppliers. So they want to buy from the hydro plant. No emissions. Okay, so they want to buy from the hydro plant and would like to buy from that hydro plant. The green load trading group calls up the hydro generator trading group and asks for a price. So he can just ask for a price. The trading group that asks a price of $60 a megawatt hour. The hydro group has to pay the transmission charges on any contract. Traders at the green load think the price is too high and say, no thanks, we'll take our chances with the market. The green trading then puts a bid. It analyzes past results and puts in a bid that will result. It believes in getting the 500 at a price below the bilateral price it got from the hydro group. So the green trading puts in a bid of $50 a megawatt hour for the 500 megawatts. Okay, so that's the deal. He called up and they wanted too much money, so they said nuts. And there's I should have said there's a box over here where everybody is in contact with this, and these are supposed to be dotted lines. And this is the market here. Oh, watch me. I found out long ago that writing with a mouse is very hard. And it looks like I'm shaking here. That's the mouse. Here's the market. And so instead of just this instead of this direct one, oh, look at this. I have colors. See that? So that's the telephone. That's the bilateral is over the green. That's the telephone. He's going to rely on the market, and everybody is in contact with the market. And the market says, okay, I got bids to sell, bids to buy. Okay, let's No, I'm trying to delete this stuff. Annotate, oh, clear all. Okay. So the bilateral case, in this case, let's analyze this. The transaction is done completely outside the market, and only the value that is actually transacted gets superimposed on the transmission system. The price for the market sold to the green trading company by the hydro is 60. The market doesn't care about what that price was. I mean, it might care on the side, but formally it doesn't care. What it cares about is how much power are you going to try to send from here to here. Now, of course, some of it goes across here and some of it comes down here and back up. So the generator has to pay any transmission charges determined by the result of the auction. So the price is, and for all I know, the price is kept private. They don't reveal it. So the results are as follows. Here's 500 megawatts, and I want to go back one page. These are the max flows, 1,000, 600, and 700, and we're transmitting 500 megawatts plus there's 1,000 megawatts out of this generator here. If you notice, we already have some generation and load going on, so we need to account for all of that. And when they put this 500 that's going in here, let me change my color. Oh, I love this color. So let's say we got this red one coming in here and out here, and it's adding to the system. And so these are the new flows. The new flows are the blue here. Oh, look at the colors. I don't know that you can do this in PowerPoint, but it's fun to do it with colors like this. At the University of Minnesota, when they built our new building, there was no blackboards. Everything was whiteboards, and suddenly you could use color markers. They were much more easy to use than colored chalk. We never had enough colored chalk, so we played a lot with colors. So anyway, these are the flows. So here now, the hydro generator is taking, the hydro trading group places a bid. This is done giving the auction. So here's the cost of the hydro, and the green load. Now, this is the market case. I'm sorry, the market case. The hydro places a cost curve. Okay, so that is a cost curve. Okay, you notice that is a I don't know what I'm doing here. I'm going to clear it all. Now that's interesting. I now have no way to clear it. Down to the bottom. So there's a cost curve. He says to the market, I have this cost. And the green load submits a bid to buy function. And so there's a bid to buy. Now you notice that it's a negative function, and that's because he's buying instead of and we're going to switch the page to the final page. Other generator cost functions and so forth are here in the data, and the market auction results with the hydro generator and the green load as part of the market R. Okay, this is the market case. The market case, he only sells 45 megawatts, not 500. But the load doesn't get, there's no transactions. The market participants are, and there's nothing in here. This is the result of the market for the buy and the sell. He didn't get to buy anything. In fact, the hydro was just part of the market. So the hydro gets to sell 45 megawatts, and note that the hydro generator only sells 45 and the green load receives nothing. So last of all, you should plot the demand and supply curves for the market case. Does this help to see why the result is shown? For the bilateral case, the dollar income received by the hydro generator and transmission charges, the net income for the hydro generator. For the bilateral case, the dollar paid by the green load. Calculate for the market case the dollar income by the hydro. We know that the green load had the opportunity to make a transaction and chose to go to the market. Was this a green load's decision the right one? Okay, that's what you're asked to do, and you're going to read the chapter and ponder this for a while, and then when we come back. So what time have we got now? We got 2:04, and we'll give you okay, it's Friday afternoon. Do you want to come back at 3? Do you want to come back at 2:30? Somebody give me a text message here. Any feedback? I'll work with you either way. Okay. Not hearing anything. I have no.
I think, how long?
Once again, this is Bruce Wallenberg. This is lecture 15A.
Somebody's starting the lecture.
Yeah, sorry.
And auction.
And
First,
auctions. I could give you an hour to do the video and then start working on the problem, or we could cut it short if you want to. It's up to you. I can go till 3, and then we'll start talking about the problem at 3 o'clock. That should give you some time to look at the video and then work on the problem. Okay? All right. So I will type this in here. I will 3 p.m. and we'll go through the rest of that problem and finish up for today. It probably will take till about 3:30 or 3:45 at the most to finish that problem. Okay? Okay. Well, there was a question about what video to watch. It's right on the schedule here. Module 15, interchange pooling brokers auctions. I hope the one answer sending the question figured that out. The question was sent a while back, 206, so, or 206, yeah. So I hope that was straightened out. Okay, I'm going to do is I've got the power markets problem solution. I think that, yeah, that's what this is. So what we did to solve this problem, and if you're looking at this and you've tried to wrestle with it a little bit, you're going to look at me or think about this and you're going to say, what's the matter with this guy? He gives us this problem and then he uses a computer program to solve it. That anyway, what we did was we used the since we only have the linear data, we solved with the QP DC load flow, DC OPF with the QP and linear power flow. Okay, and we imposed a transaction. So this is a transaction here. That's a transaction plus 1 to 2. That's this transaction that we imposed on the system, and we have this bilateral transaction here. Remember, let's see, let's just go over here. Of course, it this thing leaves the, so 1 to 2, okay? And he's trying to buy 500 megawatts, right? So base case transmission loading, case without contingencies, etc. So we did a bilateral, and we have various bids, okay? I'm going to show you the bids down here. I'm trying to figure out here are the generators. So you can tell they're generators because the B is it's a quadratic. There's no, pardon me, it's linear. It's A plus B plus C. A is the constant, B is linear, and C is a quadratic. So it's A plus BP plus CP squared. These are the B and C constants. The A makes no difference whatsoever, so we leave it out. And these are the generators. And then these two are the loads. So if we go back to this, we can see that we have a load of 1,500 megawatts and a load of 1,000. There they are out there, and we have generator 1, 2, 3. Okay. Now the reason I did this is that I need a baseline to figure out how much the transmission charge is. The transmission charge is the megawatts that you're trying to send through the system times the difference in the difference in the marginal prices, the bus marginal prices. So there's the total cost, the total generation bid, the total load bid, etc. Now the bus lambdas are over here, 2654.82. Here's the transmission on the system, and we'll come back to these in a little while. Now the market case is different, and in the market case, there's no base of 100 megawatts or anything, and we're going to have a bid in here. Let's come back to this. So here are the generators, and here are the loads. Notice that we've got a fourth generator, and it actually appears as bid number 1, and that's the, let's see, how much does he offer to bid? Get out of here. He bids at 60 plus 0.002. And he can go up to 500 megawatts. Anyway, he puts his bid in here, and these are the other generators, and then there's the load comes in for 1,000 and or 100 here, and he tries to bid. And we get different lambdas down here, and then so the hydro generator to the green load 100 megawatt transaction. Now here's something I have to do something about. This should be 500 megawatts. So I'm thinking that my answer sheet here is not correct, which is not funny if you're a student and you're trying to figure out how to do a problem and the answer sheet doesn't relate. But in any event, what we did is we varied the price, and then we said what the transmission charge is the difference in the is the difference in the bilateral, it's the difference in the bus marginal prices times the 100 megawatts. And then we said, okay, that's the transmission charge, and this is what the green load purchases 100, but the cost goes up depending on what price. So these are all the prices that the generator could ask for 100 megawatts, and its income would be 100 times 10, 100 times 20, and so there's the income. they would pay the transmission charge, which would have been the same amount. So you would hardly make anything if you charged 10 or 20. You'd make a little bit over here. Here's the profit. It's a loss here. And this is the cost to the green one. So the transmission charge, there's the difference. This is the here it is. There's the difference, 54 minus 26. The difference in the bus marginal prices times 100 megawatts. That is the cost to deliver that the transmission owner is going to charge you. And then the I gotta clear this, it's driving me crazy. So at 28, if the price were 28 right here, it goes from negative to positive, so it's 0. So that's the break-even price for the hydro, and that's where he makes no money. At 54, the generator would make $2,600 at 54, which is the same as the market, and the load would pay $5,400, which is also the same as the market. So the price range for the guy should have charged something less than 54 but above 28, and he could have made some money. And that is the analysis. So I'm thinking the answer sheet here says 100, whereas the problem says 500. And what I'm thinking of is that this problem maybe got changed in the book without, and I'm using a copy that's pre-publication. And I'm just looking that up in the book to check this out. Nope. So what we've discovered today is that my answer sheet for this problem is wrong. Anyways, that's a shame. I will have to change that and get that into a new answer sheet. Okay. The issue of the markets, there was a lot of griping and grumbling among engineers that I knew in the Minneapolis area about deregulation. They thought that they had this beautiful power system, making money, et cetera, and that the markets and the deregulation was going to wreck everything. I mean, it certainly changed a lot of things. But my opinion is that the entry of the economists looking at the power systems, for one thing, it made putting new kinds of generation much easier. People would let's just stop this and oh, I'm sorry. People would easily that's not hard to see that the electric utilities would build power plants and they'd keep them running for 40 years. That was kind of a target number. Nowadays, that's not so much the case because new companies will come in and build more efficient generation. And this forced everybody that's in the business to be more efficient, and that's good. That's really good. Behind all of this, and I say this a little bit tongue in cheek, but also I'm not so much aware of all of it. But I suspect that this 40 years and so forth construction had a lot to do with the regulators as well. And I can just throw that out as a possible cause. So that the deregulation, we have seen a lot of new kinds of a lot of combined cycle power, and of course wind and solar and things like that would be built. Had they not deregulated, I don't know how they could have gotten that done, because the generation was always built by the utility. And if they didn't want to do it, well, okay, they'd have to get into long battles to get things done. Whereas now, they can build these things. The wind farms are often independently owned. There's one down near Austin, Minnesota. The wind farm was anyway. When we visited it, it was owned by Florida Power and Light. So you know, it's a generating company that's owned by Florida Power and Light, and they're building stuff in Minnesota, wind farm. So that kind of thing would not have happened without this. I don't think anybody can make the case that the system is any less reliable. It seems to be amply reliable. One of the things that has resulted, there's a great push today for looking at the cyber attacks and how to make the system more resilient and well, that's a word I don't like too much because it's ill-defined, but more reliable in the face of cyber attacks. But now you have structures through the government and through NERC that are different. They operate differently. They're going after that problem big time. When you hear books, there's books and TV programs about power systems could be attacked. And they act like it could be tomorrow. And they act like the utilities or the electric companies are doing nothing. Well, that's ridiculous. They're doing a lot. And so, don't be concerned about that, about the cyber not being looked at. NERC has lots of work going on in that area for reliability, but just generally the reliability of the system is certainly on the mind of everyone. And the open market, I think, has been a fairly successful. Who benefits the most? Aha. And that's a question that's difficult to answer, and I don't know where we can get at an answer as to who benefits the most. Did the big load buyers, the big auto companies and steel, and whoever are big huge buyers of power, did they get cheap deals for cheaper energy while the consumer is paying more? No, I've never seen such an analysis done that's been published. The big battles going on today are whether we can live on wind and solar and start getting rid of all thermal power plants. Well, frankly, the answer to that is no. And it's a simple matter of wind doesn't blow all the time. The sun isn't out at night or when there's a lot of clouds. And there is no storage technology that is economical today. Maybe that'll change. So if it changes, if we had lots of storage, everything about the electric utility industry would change around. They would build lots of storage near the cities, and you wouldn't need the amount of transmission you do, because you could transmit at a steady rate night and day and just use the storage when your load was low. and then draw down the storage when the load was high. So you wouldn't need the peak, the transmission wouldn't have to carry the peak. So that would change the economics completely of power systems. Okay, so the operations of the power system are still a very, very important topic. I am trying to think. I may have some.
Professor, quick
Yes.
question. Will the video remain on the web? Because you mentioned some material will be taken out from the web.
I heard. Oh,
The
no,
video.
the material that was posted for you is gonna go away. It's not gonna be there after the course ends. But there will be a video of the course. That's as much as I can tell you. I requested that a lot of the material not be left there for a long time because of the material was copyrighted.
Okay, well, thank you very much. I have to go. I really appreciate, I enjoy very much the course, and I appreciate your personal interaction, Professor.
Okay, thank you. If there's any other comments, please, please come forth. I'm trying to see, I have, let's see here. These are views. Here we go. This is some examples of here we'll start with this. Here's an example of some large control. This is the California ISO. I think this is an earlier version, but this is typical of an operating room with screens and a huge map board. The map board is mostly static, but it has some lights on it to indicate special things on there. This is a different view of that same California one. This is one in Florida. This is one that's got, instead of a static map board, these are displays. So they just display the map board. I think that may be in England. This is a small one. This is Detroit Edison. I was there and they sent me some pictures. That's Detroit Edison again. You can see how big these rooms are. This is multi-floors. There's a guy up here literally 10, 12, 15 feet above the floor so he can see everything. That's another display from Detroit Edison. This is a picture of what it used to be like. And now what's changed so much? Well, these are the monitors that we used up until the 1990s. This is PJM. They even give you an indication on there. Look at these cabinets that they had are beautifully crafted wooden cabinets. This is San Diego Gas and Electric. Again, older. Notice the cathode ray tubes, and that's all been replaced by the screen sharing has stopped as shared window is closed. Well, okay. Um, there we go. Now this is going to be really funny. Do you see that? Let me stop sharing and bring that back up. Do you recognize him? This is a publicity photo from California ISO when this guy was the governor of California, okay? Name's unsaid. It's another picture of a control center. Notice the screens. This is First Energy down in near Akron, Ohio. Look at the screens. Lots and lots and lots of screens. So, and this is what they look at in the control room. This is a substation one-line diagram. They show various devices like capacitors and grounding switches and so on and so forth, and circuit breakers in the control room. This, I don't know where this is, but this is also a big, but this is an older one with the cathode ray tubes. Now see, we go to screens, flat screens. And this guy has what, 3, 4, 5, has 7 of them lined up. And they can see whatever they want. And then they have a giant screen up here that's actually an active screen. So they can put colors on there, anything they want. Notice over here, this is probably a weather map, or this is too. Utility companies are always concerned about the weather. Oh, this is ISO New England. It says up here on this work right underneath the ceiling, ISO New England, outside of Springfield, Massachusetts, and that's the ISO New England screen. They're one line on the screen of their operators. There's a picture of the computers. What I told you is that all of these centers use a lot of microwave communications. This one is a modern one because it's using flat screens. That might be New England again. I think that's an older one, but I just acquired all these pictures and used them in talks a great deal. So let me see here. I only see a few people still logged in, including my faithful assistant, Jayram. I thank you so much, Jayram. You did an excellent job to keep this course moving along. I think the chat window is best. Yep, we're done with it. So for those of you that are still hanging on, if you have other questions, feel free to email me. But if I don't hear from you, I'm sorry. I'm saying goodbye to everybody. So have a good weekend. And we're having beautiful weather here in Minnesota right now. We had some rain last night, but it's been cool and just beautiful today. Okay,